friends. Hi, hello friends. Welcome to the session. In this session, we are going to talk about thermal stress. Okay. First, let's see what is a thermal stress. Thermal stress is nothing but the stress that is induced in a material due to change in temperature. What? Does a stress induced? The stress induces due to temperature change. In the previous class, we know that when external force is applied, stress induces okay, but due to temperature change also there will be a stress. Okay, due to temperature change there will be a stress. Let's see how it comes and what all cases it comes and all. Okay, there is a material. We'll just make a neat diagram of it. Okay, there is a material. Let it be steel. It can be any material, but I'm just taking a steel as an example. We are heating up this material. It has no constraints in both the directions, so there will be no stress for induced if we apply temperature. If you apply change in temperature, we are applying heat and there will be a change in temperature. First it will be in T1. After applying the heat, it will be in T2. But there is no change in there is no constraints. That is, there is no restriction on both the sides. So what happens? The material will be allowed to elongate. Let this one be delta L1, then this to be delta L2. The delta L be sum of delta L1 plus delta L2. Delta L means change in length. Okay, the original length be L and the temperature, change in temperature will be T. Okay, in this condition, will there be any thermal stresses? No, definitely there won't be any thermal stresses, but there is strain. There is elongation, so there is definitely a deformation. If there is deformation, then the strain automatically comes. This strain is called thermal strain or temperature strain. Thermal strains and they are also called as temperature strains. Okay, we'll just see how much strain is occurring if a material is heated. First, let's get to the expression for delta L, change in temperature, change in length. We have a original length L and there is a change in temperature T, and every material has a coefficient of linear expansion. If there is more coefficient of linear expansion, then the more the material gets elongated. If there is less coefficient expansion, if the coefficient expansion's number is less, then what happens? The material does not expand too much. Delta L. What is this delta L formula? Length into temperature into that coefficient linear expansion. We can write it as T. Okay. We know strain is equal to delta L upon L. Okay, what can we write this? Take this L down and it becomes alpha alpha T. This is the expression for thermal strain is equal to alpha T. Okay, now we are restricting or making the motion constrained. We are constraining it the material on both the sides and we are heating the material. This time there is definitely elongation is not possible and there will be induced stresses. That stresses are called as thermal stresses. How to find an expression for this? We know stress upon strain is equal to Young's modulus. Okay, in the previous session we have thought of Young's modulus. Okay, so this thermal stresses will become thermal strain into Young's modulus. Okay, let's wrap this. We saw the expression for strain, that is alpha T, and this is E Young's modulus. This is a expression for thermal stress. We saw what is thermal stress and what is thermal strain. Okay, and we saw the expression for elongation delta L. Now see, if I'm rubbing this and there is a material, this material is only constrained in one direction and partially constrained on this direction, on this end. That means if elongation happens, it moves for a little bit extent. We are applying heat. This is fully constrained or fixed. This is partially fixed. What happens? On applying heat, in this condition there is no heat applied. When on applying heat, this side is partially fixed. What happens? There will be extension. This partially fixed wall, maybe a wall, okay, consider this as a wall only, partially fixed wall. What happens? There will be elongation till here. Let this be delta and this get constrained in one position. So how much time it can extend? It will be constrained in one position, and we'll just take this as delta, and this is the original length. This topic comes under support yield. Okay, in thermal stresses only comes under support yield. For this strain, expression for strain is given as we just saw in the previous session, not previous session, in this session only, stress. We just saw stress as, we just now saw stress as equation for stress as thermal stress as alpha TE, okay, and thermal strain alpha T. In yielding concept, Just observe cleanly. When yields are applied, this is without yielding support. This with yield support strain will become alpha TL minus delta by L. Alpha TL, change in length, minus this yield length. This will be some yield length delta minus this delta to original length. This will be the equation for strain, change in length to original length. Okay, we are going to multiply this with with Young's modulus. This becomes the equation of thermal stresses. Note the formula, very important formula. Okay, now let's see what is coefficient of linear expansion. Okay, what is alpha? Expansion, coefficient of linear expansion. If I am asking you that I took a steel rod, steel bar, okay, I am heating it, it will extend to some position. I am taking this steel, I am taking a invar is also a metal. I am taking it, I am heating it. It will also extend to some material by some extent, but not as steel. I am taking aluminium. I am heating it. It will expand so much more than steel. Okay. Why so? This there are materials only, but this is expanding. So this is expanding to some extent. This is expanding little than steel, not little. This will be expanding only to some extent. It will expand very in few conditions, very high temperature difference. It will be expanding, but aluminium within small. If T1 is 30 degrees Celsius and T2 is 90 degrees Celsius. Within some change in temperature also, it will be expanding to some more large extent. Why so? Why the materials having or expanding to different extents when there is a change in temperature? Let the same change in temperature, T1 be, it's out of frame I think. For same temperature, let this be 10 degrees Celsius and T2 be 60 degrees Celsius. In that conditions, steel will be expanding till this, okay, till this end, and the invar will be expanding just some, and the aluminium will be expanding so much, maybe till here. Okay, consider why the question arises, why the material expands, so various materials expands in various size. Why? The reason is because of coefficient of linear expansion. Note it. Let's write first invar, diamond, steel. Then what will be writing? Aluminium, I think. Steel, copper, brass, aluminium. One point two, 1.1, 12, 16, 20, 23. Just put 10 to the minus 6, 10 to the power minus 6 into 10 to the power minus 6 into 10 to the power minus 6 into 10 to the power minus 6. Its all unit is per degree centigrade. Alpha's unit coefficient of linear expansion is per degree centigrade. Okay, its unit is per degree centigrade. The value of alpha for invar is 1.2 degree centigrade. Value of diamond is 1.1 degree centigrade. Value of steel is 12 degree centigrade. Sorry, 12 into 10 power minus 6 degree centigrade. For copper, alpha for brass, alpha for aluminium. Say which material. Okay, just first I will help you to memorize this numbers. For invar, this is 1.2. For diamond, 1.1. For steel, 12. Copper, 16. Brass, 20. Aluminium, 23. This invar. Okay, now I'm asking a question that among these materials, which has the lowest coefficient of linear expansion? Among these materials, which has lowest coefficient of linear expansion? Diamond. Okay, diamond has the lowest coefficient of linear expansion among all materials, but diamond is not a metal. Okay, not a metal. Among metal, which has the lowest coefficient of linear expansion? Absolutely invar. Among metals. Okay, which has highest coefficient of linear expansion? Definitely aluminium. Okay, aluminium has more coefficient of linear expansion. Now I am asking you, we have to make a measuring tape. Okay, I want to make a measuring tape. That measuring tape must, I am using it in what I am going to Sahara Desert. I am using it, and I am going to Himalayas. I am also using the same tape, but it should not make any difference in both the conditions, right? What happens if this material is steel? When I go to desert condition, there will be so much heat, and what happens? This gets elongated. And when I go to Himalayas or Antarctica, what happens? Cold regions. What happens? This gets contracted, and I'll get definitely wrong value in this both the conditions. Okay, you get elongated. Tape gets elongated. This compress. Okay, compress, contracted, anything. So I will not be definitely using steel or steel tapes. But which material I'll be using? I'll be using invar. Diamond I can't use. Okay, it's not a metal. I'll be using invar. Invar has the lowest alpha coefficient of linear expansion, that is 1.2 into 10 to the power minus 6. So it will not be expanding too much, not be contracting too much when the temperature changes. So on measuring conditions, we'll be using invar. If I want to expand, what will be I using? I'll be using aluminium. Okay. So whenever a question arises in MCQs, they'll be asking. MCQs is multiple choice questions. In multiple choice questions, they'll be asking, name the metal having least alpha value. Coefficient in expansion, they'll be saying option A will be given as aluminum, option B will be given as copper, option C will be given as brass, option D will be given as our invar. What you will be choosing? You will be choosing D. If the same question is having high alpha value, what you will be using? We will be ticking the option aluminum. Okay? Okay, then now I am asking you a question. What is the alpha value of aluminum? Option A I'll be giving you 16, option B I'll giving you 18, option C I'll giving you 12, option D I'm giving you 24. What you will be choosing? You will be definitely choosing 24 because aluminum has the highest alpha value. But if D option will be given if C is given as 24 or 22 something and D is given as 50, what will be you choosing? Don't say that I'm choosing 50 as this is aluminum has the highest alpha value and this 50 is the highest alpha value given, so I'll be choosing 50. Then the answer becomes wrong. You'll be choosing 22. You have to know that the alpha value does not go near 20 50s and all. It will be going till 20 to 25 only. If this will be given 12 and giving me 20, what you will be choosing? You have to choose 20 as alpha is the highest for aluminum has the highest alpha value. Aluminum has the highest alpha value, so choose the greatest number but range between 20 and 25. Okay. Now we will see what the units for thermal stress. What I told you, thermal stress alpha T into E. For alpha we know unit is per degree Celsius and this is degree Celsius or Kelvin, both gets cancelled and we'll get Newton per meter square for thermal stress. Thermal strain E by stress by strain is equal to E. So this is not E by strain, it will become stress by E. Newton per meter square, Newton per meter square, both gets cancelled and strain has no unit. Okay. I know you guys that you will be very interested with numericals, okay, rather than theory. So I'll be giving you a numerical problem. Consider this is a steel rod. Its diameter is given 3 centimeter. Its length is given as 5 meter long. And there are the initial temperature is 95 degrees Celsius and there is T1, and after sometimes is given as it is lowered to 30 degrees Celsius. Conditions: 1. Ends do not yield, and 2. Conditions that ends yield by 0.12 centimeter. Okay, take E is equal to Young's modulus is equal to 2 into 10 to the power of 5 meganewton mega Newton per meter square, and alpha is given as 12 into 10 to the power minus 6 per degree centigrade. Okay, you have to find stress and strain. Question. First, change in temperature will be noting as 95 minus 30 is equal to 65 degrees centigrade, and area is equal to pi by 4 d square, and we know pi by 4 into 30 centimeters only, I think. Yeah, it is given in the 3 centimeter. We will be taking in mm is 30 mm, so we'll get 225 pi centimeter square, sorry, mm square. We took this in mm, so mm square. Area we got it. We know length of the rod, L is equal to 5 meter. They given that 5 meter, so 5000 mm. Diameter 3 centimeter, that is 30 mm. Okay. Conditions 1, not yield conditions. Stress is equal to alpha TE, we know, was 12 into 10 to the power minus 6, temperature is 65 degrees centigrade. Need not make it as in Kelvin, okay. You know, 2 into 10 to the power 11 Newton per meter square will get. Mega is 10 to the power 6, so 10 to the power 5 into 10 to the power 11, 6 is equal to 10 to the power 11. What we have, we'll get the value of 156 Newton per mm square. We got this value in positive condition, so this is considered as tensile stress. If this condition is given in minus sign, minus 156, if we got the answer as minus 156, then we will take it as compressive stress. Okay. We got one answer. We know strain. The question they did not ask as strain, they asked as pull of the rod. Okay. Pull of the rod is equal to stress into area. If you multiply stress and area, if you multiply stress with area, we get 156 into 225 pi, and the value we get as 110,269.9 Newton. Okay, this will be the pull of the rod in no yield conditions. In yield conditions, we get, if the ends yield by 0.12 centimeter, we use this formula, stress is equal to alpha TL minus delta by L into E. Okay, what happens? 12 into 10 to the power minus 6 into 65 into 5000 minus, that is given in centimeter, so millimeter will become 1.2 mm divided by 5000 into value of E, 2 into 10 to the power 11. Two into 10 per 11 for Newton per meter square, but we are seeing in Newton per mm square, so we will be taking this as 2 into 10 to the power 5, okay, Newton per mm square. What will be the answer? The answer, I guess, comes as 3.9 minus 1.2 by 5000 into this 2 into 10 to the power 5. On equating this, we get a value as 108 Newton per mm square. This is the value of stress, thermal stress, if the ends yield by 0.12 centimeter. Now we'll see if the ends yield and there is a pull of the rod. Pu will pull of the rod. What again? Stress into area. We got stress as 108 into 225 pi. We get 76340.7 Newton. This will be the answer. They will ask in GATE as 2 mark. Sometimes they'll be asking just stress and they will be giving you 1 mark. Okay. That's it for today. Bye. Guys, if you like this session, please like and share with your friends, and also please subscribe. Liking the video will give me more motivation, and I'll be providing you more videos with enthusiasm. Okay. Bye guys.